So those are the two problems with silicon. So what are people doing to address that? Well, there's a lot of research, a lot of it even in California, of people trying to solve this problem. One of the few non-silicon ways of making solar cells that's been actually made it to market are known as thin film solar cells. And so instead of using something like silicon to absorb the light as the semiconductor, they use an alloy of copper, indium, gallium, and selenium. And by changing the ratio of all of these things, they can tune what color of light the material absorbs. This material is off the chart, wrong way, off the chart here. It would be up closer to about here, even up above indium gallium arsenide. And so this material, I keep going the wrong way. This material is extremely efficient at absorbing light. And what's nice is it absorbs light in just the right region for sunlight. And so this material can make very efficient solar cells and be very cheap. What I'm showing here is just kind of a cross-section, a cartoony cross-section of one of these solar cells based on this material. You can see that the overall thickness, so if I were to add all of these up, would be about 5 to 6 microns. The width of a human hair is about 50 to 100 microns. So this would be about 10 times thinner than a human hair. Silicon, on the other hand, has to be closer to 100 microns to be able to absorb enough light to work as a solar cell. So again, this is about 50 times or so thinner than a silicon solar cell. So what that means is it's cheaper because we use less material. We don't have to have 100 microns, we can use 5 to 10 microns instead. So we use less material. In addition, most of these materials are pretty easy to find. And it also, because this junction, which is between the cad sulfide and this CIGS right here, because all of this material is so close to this junction, it ends up being more efficient, and we don't have to worry about having a very pure, very crystalline material here. And so this type of solar cell ends up just being a win in every possible case. It uses less material, it absorbs light better, and we don't need to be as pure when we make it. There's still a few problems with this. For instance, this indium. Copper's not so bad, selenium's not too bad, and gallium's not too bad. Indium is extremely expensive. Indium's one of the rarest materials on Earth, one of the rarest elements on Earth. And indium ends up being one of the primary costs for things like plasma televisions. It's so rare, and everyone wants a plasma TV, so it makes it a little expensive to put into something like a solar cell. So just due to market forces and rarity of this indium, this would fall into the second generation solar cells, but if we could make this cheaper, we could make it even more cost efficient. So there are a lot of people who are trying to find other materials to replace this copper indium gallium diselenide. So that's what some of the research going on in solar cells is. The next is this idea of a dye-sensitized solar cell. And so previously, when I was talking about explaining how solar cells work, I talked about semiconductors. Turns out you do not have to make a solar cell out of semiconductors, or at least not completely out of semiconductors. The idea behind a dye-sensitized solar cell is instead of using a semiconductor to absorb the light, let's use something else. Let's use a dye. So let's, for instance, people's blue jeans are blue. That's because it's absorbing light. Well, if it's an organic dye and it can absorb light, maybe it can absorb light and be used in a solar cell. And so a guy in Switzerland, whose name is Michael Gretzel, figured this out in the late 90s, early 2000s, that this can be done in a pretty efficient manner. These solar cells aren't as efficient as semiconductor solar cells. They also have a problem with bleaching. For instance, if you leave blue jeans out in the sun too long, they go from being blue to being white. As anyone who's ever done that knows. So these organic molecules that are absorbing light burn out too quickly. And so this is the potential for preparing very cheap solar cells, but the problem right now is trying to find the right dyes. And that's what a lot of people who are working on this type of solar cell are trying to do. The other problem is, right now at least, this uses a liquid cell. And so to get the electrons to go one way and the holes to go the other, which we still need that junction, in this type of cell, that junction ends up being a liquid junction. And not only that, this liquid tends to be pretty caustic. It's very reactive, and so if these solar cells break, they eat holes. This liquid eats holes and things, and so it's not the kind of thing you want on your roof. Worry about it, breaking and then eating a hole through your roof. So people are trying to find ways to replace this electrolyte with something that's a little bit less reactive and a little bit less likely to eat through your roof. And kind of one way that people are trying to do this are known as organic solar cells. So most semiconductors are made of things like silicon or copper or indium, a lot of metals and metal oxides and alloys of different materials in the periodic table. However, I want to say in the mid-'80s, some physicists at Santa Barbara found that by making organic molecules, so basically carbon, hydrogen, and oxygen, and arranging them in the right way, they can make semiconductors that are made out of carbon. And so these are called organic semiconductors. And in the 20 to 30 years since this has been discovered, there have been a lot of new organic semiconductors that people have discovered. And so if it's a semiconductor, people are like, hey, we can make a solar cell out of that. And so what I'm showing is a cross-section here of one type of solar cell based on organic materials. There are two nice things about organic solar cells versus inorganic solar cells. One of those is that these organic solar cells, because they're all based on organic chemistry, are the kinds of things that you can make and make at a very large scale. Organic chemicals, people make at very large scales all the time. And so there's a large industry built on just making organic semiconductors and doing it cheaply. And so the materials for these solar cells tend to be very, very cheap. The other nice thing about this is that organic materials are generally very flexible, while inorganic materials are very brittle and tend to break. And so there are some people who have the idea maybe that this can actually be even just a paint, where you paint on a solar cell on the side of your house, for instance. And because it's so cheap, we don't have to worry about the efficiency so much. That's the big drawback for organic solar cells, is that they're very inefficient. They don't absorb light very well. Electrons and holes don't move through the material very well. And the one-way junction that pushes electrons and holes in the opposite direction doesn't work very well. It lets a lot of things back through the wrong way. And so right now, the majority of research on this is how we can take these cheap materials and make the organic solar cells more efficient. And then finally, I'm sorry, not finally. Well, I guess in terms of solar cells, the last thing I'd like to talk about. So this is actually work that I do at UC Merced, so I have to shamelessly plug my work at some point, because I haven't done anything else as of yet. And what I do, and what a lot of researchers do in this country, is try to find ways to use even less material than you would in a thin film solar cell. And we do that by using what are called nanowires. And so what I'm showing here is a nanowire or it's actually this one, that copper indium diselenide material from the thin film solar cells with a gold nanowire sticking out of it. And the reason we want to do this is twofold. One, because this gold nanowire is predicted to help light absorption in the semiconductor material. So having this metal here actually makes the semiconductor absorb light even more efficiently than it already would. The second reason is because this semiconductor material is going to absorb light, and so we want all of the light absorbed to be very close to the metal wire that's going to collect the electricity, because then we don't have to worry about the electrons in the holes recombining. If it's close enough, it's just going to immediately go right to the metal, and the electron's going to go the other direction, and we're not going to have to worry about how efficient or how good our one-way valve is. And so by using these nanowires, we're hoping that we can make solar cells even cheaper than they already are as thin films, but maintain the same efficiency. We're not there yet, but hopefully we'll get there very soon. An alternative idea with people using solar cells, there's some really cool research at Caltech by a couple of a physicist and a chemist, where they take nanowires that are still silicon in this case. So this would be a P silicon. This blue would be the N silicon, just like I had before. But what they do is something a little bit different. So light comes in, shines on the material, creates that electron-hole pair. But in this case, instead of becoming electricity, what they're trying to do is turn this into a fuel. So they're using the electron and the hole that are created in this material to turn water into hydrogen and gas, hydrogen and oxygen. And then they would like to collect the hydrogen and use that to fuel cars. And part of the reason for this is, as I mentioned before at the beginning, the sun is shining when we don't need the light, right? We don't need the electricity during the day. Well, in darker rooms, I guess we do. But a lot of our electricity is used at night when the sun isn't shining. So we have to find a way to take the electricity or the energy that's given to us by the sun and store it somehow. So they're hoping to store it as hydrogen and oxygen, which we could then later burn to form water. So a closed cycle, a very clean cycle for producing electricity. I'm going to talk about something else, though. I'm going to talk about storing this as batteries. So all of my research at UC Merced is focusing on either solar cells or batteries. So I've told you about solar cells. I'm going to, hopefully quickly, because I've taken a long time so far, talk about batteries. So what is a battery? Turns out a battery is just kind of applied chemistry. It's actually one of the first fields of chemistry, electrochemistry, to really be discovered. And it's also one of the more practical fields of chemistry. So what I'm showing here is the periodic table of elements. Hopefully everyone has seen this before at some point, but maybe not. And it turns out there's a lot of information here. And one of the nice things about being a chemist is you can glean a lot of information. You can read this table and make predictions from it. One of the things that's important to know about the periodic table is that everything in this corner really wants electrons badly. Everything on this side does not want their electrons. They're willing to give it up. So you can kind of think of this as these are the bullies and these are the kids that get bullied and give up their milk money. Fluorine will come in and take an electron from any of these guys, and these guys are perfectly happy to say, here, please leave me alone. Another way to look at this is in this table right here. And so what I'm showing is kind of a desire for everything to want an electron. And we can rank them. There are different ways to look at this. But if we focus on two different things, for instance, we focus on chlorine here and sodium here, we can see that, well, if we could read this, this would be plus 1.36, and this would be minus 2.71. And so these are in volts. And so hopefully everyone remembers a little bit of electricity and understands that volts are in some way related to electricity. It turns out if we were to take chlorine and sodium and mix them, it would release energy. There we go. Oh no. Okay, well, I'll have to fix that in a second. So if I were to mix sodium and chlorine, because the chlorine really wants an electron and the sodium is perfectly happy to give it up, we'll get a sodium cation, or a sodium positive, and a negative chloride. The energy that's released in this reaction is about 4 volts. So what is 4 volts? Let's take a look. So this is a flask filled with chlorine gas, and we're going to put some sodium in there. If the movie works, sweet. I did not do this in my lab because chlorine scares me. So someone else was dumb enough to do this. You'll notice also that there's some sand down at the bottom here. That's just to keep it from getting too hot and breaking the glass. So there's the sodium metal. The greenish stuff is chlorine gas. There's nothing happening yet, because like all reactions, you have to kickstart it. You have to give it something to start the reaction. And so we're going to add just a little drop of water, and that's going to start the reaction when it gets to the bottom and drops on the sodium. And that would be 4 volts of energy. And that was a pretty small piece of sodium. And so you can see that 4 volts, or at least hopefully you can see that 4 volts is a lot of energy. The question, though, is how do we harness this? I don't think anybody wants this to happen in their cell phone, especially when it's in their pocket. So how do we actually control this?